Okay, in this lesson, we're going to talk about the Cauchy stress tensor and its invariants, and we're also going to look at how those invariants can be used to really represent fundamental soil behavior by looking at stress paths for a drained direct simple shear test. So first, let's talk about the Cauchy stress tensor. I think this is basic, but and probably repetitive, repeating some information you already know. But it's important to revisit it because geotechnical engineers are often a little bit cavalier about how they handle stress. And so we need to really review the fundamentals here so that we know exactly what we're talking about. So here's the Cauchy stress tensor. Okay, it's a symmetric 3x3 tensor, and I've represented it here in x, y, z coordinates, which are just regular orthogonal coordinate system. So when I say symmetric, I mean that sigma xy is equal to sigma yx and so forth. Sometimes sigmas are put along the diagonal and taus are put in the off-diagonal cells, but I'm just using sigma to represent all the stresses here. Okay, now if we have a known stress condition, say vertical, horizontal, and horizontal the other way, and then shear stresses in all those planes, we can rotate that soil element and get a new stress tensor, right? The stress values change upon coordinate rotation. So if we change coordinate systems, the values change. And I actually have a tool that you can use to study this. So let me go over, I have a URL put in the notes right here. And I'm going to go over to that website now. And let's see, here it is. Actually, there's two different pages, so I'm going to go back to state of stress. Okay, so if you go here, I have a YouTube video you can watch. It's going to summarize a lot of the same things in this video. But here's an image from Wikipedia that shows what I'm talking about. Here's the original stress tensor, and then when you rotate, you get a different stress tensor on rotated planes. And we can define the stresses on the rotated planes if we know the angles by which we're rotating all of the coordinates. And so you get these primes. Okay, primes usually denote effective stress in soil mechanics, but here I'm just denoting a stress rotation from like the x3 to the x3 prime axis, and similar for x2 and x1. So the angles are A11, A12, and so forth, and we can then multiply through by this A tensor and the original sigma tensor, and we get the rotated stress planes. So here you can try it yourself. You can come in and let's say you know that the stress tensor has 2, 1, and 1. So we already have 2 vertical and horizontal is 1 and 1 in both directions. And then let's say we want to rotate it through an angle alpha, which would be the rotation, I think, of the z plane by like, let's just say 25 degrees. And we can put the set A matrix. Now this is the matrix by which we're rotating it, and we can compute, and actually rotating about that plane didn't change the principal stresses. So if we rotate all of them by 25 degrees, we should now see a fully populated A tensor, and when we compute, we should get changes in the stress directions, right? So what we've done here is taken a tensor that has only values on the diagonal, all of the off-diagonal terms are 0, and we've rotated it so that now we have a fully populated stress tensor. There's shear stresses acting on some plane, on these 25-degree rotated planes. Of course, you could rotate through any angle that you want. The important idea is that we rotate and we get different stresses. And what I'll say is that there is a particular angle of rotation for any fully populated Cauchy stress tensor where if you rotate to those particular angles, you will get zeros on the off-diagonal, right? So we did it the other way. We started with zeros on the off-diagonal and rotated, and then we got numbers there. Well, we could go back. We could start at that first tensor, rotate by negative 25 degrees in all directions, and we would arrive at a condition where we only have values on the diagonal. Those that particular orientation corresponds to principal stress directions. And the stresses aligned with that rotation angle that particular orientation, are the principal stresses, right? And so if we want to compute the principal stresses from a full Cauchy stress tensor, it's really pretty easy. All we need to do is take the eigenvalues of that tensor. A lot of software programs have eigenvalue solvers. So if you just take like MATLAB, for example, or Python, easy to compute eigenvalues. It's no problem. So you just run the eigenvalues command, and now you've got the three principal stresses, sigma 1, sigma 2, and sigma 3. And then the eigenvectors of the stress tensor would be the orientation of the principal stresses. So it tells you which way they're pointing to. We're not going to use eigenvectors here. We're just going to use the eigenvalues. Okay, now once we have, oh, and then let me show you too. We can now compute eigenvalues in this tool. So I'm going to go to stress paths. And let me see. Okay, here we go. So we can put in any stress tensor that we want, 2, 1, 1 with zeros on the off diagonal terms, and we compute. The eigenvalues are just 2, 1, 1, right? We already started with a stress tensor that was in its principal stress directions because there's no numbers on the off diagonal terms. But if we were to come in here now and add a say 0.2 shear stress component, we compute. Now the sigma 1, 2, and 3 are rotated a little different. Notice that sigma 2 didn't change. We put the 0.2 in the 1, 3 cell. Sigma 2 stayed the same. It stayed at 1. But sigma 3 has gone down and sigma 1 has gone up. Now we didn't add very much shear stress, so those didn't change by a whole lot. You know, if we make it a little bigger, 0.5, compute. Sigma 2 is still 1, but now sigma 1 is increasing and sigma 3 is decreasing. So basically what you see is that as these principal stresses get further apart from each other, that corresponds to a condition of more shear being applied to the soil. Okay, so now what we can do, once we have those principal stresses, is to compute invariants. And the word invariant means not changing. And so what this means is that no matter how you rotate the coordinate system or anything else for this particular stress state, these invariants are fixed, right? Once you have a Cauchy stress tensor, you can compute the invariants, and they're not going to depend on coordinate transformations or anything like that. And we're going to use two invariants here. One is the mean stress, right? That's sigma 1 plus sigma 2 plus sigma 3 over 3. It's just the average of the three principal stress components. And a lot of the time we deal with mean effective stress, and you just subtract the pore pressure. Recall that pore pressure is hydrostatic, so it's acting in the same direction in all, well, it's the same amount in all directions. So we can just subtract it from P and we get P prime. Okay, so basically mean stress is like a measure of confinement, right? You can think of it like that. How much pressure is being put on the soil? And soil that's under higher confinement tends to be stronger. So it's important for us to know the confinement. And so we define this invariant. It's also important for us to define shear, like how much shear is being applied to the soil. And this is a concept where geotechnical engineers often get a little bit sloppy with their terminology. So a lot of the time we think of shear as just being like the shear we're imposing on horizontal and vertical planes on a simple shear test or something like that, right? It's like the shear stresses that exist in one particular coordinate system. Well, that's not a very fundamental definition, because if you were to rotate to a different coordinate system, they would have different shear stresses, right? We need something that doesn't change with coordinate system. And so we define the deviatoric stress invariant. And this is a really important one here. So it's based on the differences, the squared differences between the principal stress components. So you take the difference between each component, square it, add them together. Then I'm missing a bracket here. You multiply the sum of those by 1/2 and take the square root, and now you have Q, which is the deviatoric stress invariant. The way that you can think about Q is that it's like the diameter of the Mohr circle. So it says that right here. There is, of course, an important difference. The Mohr circle is a two-dimensional representation of states of stress. It only involves sigma 1 and sigma 3. Okay, the size of the Mohr circle depends only on sigma 1 and sigma 3. Some people draw in the sigma 2 as having like one big circle and then two small circles inside of it. I don't like that approach. It still is two-dimensional. when we go to Q, it's now three-dimensional, right? Because it includes the intermediate principal stress also. So it's a function of sigma 1 and sigma 3, just like the Mohr circle, but it also is a function now of sigma 2. So you can think of it like the diameter of the Mohr circle, but only three-dimensional instead of two-dimensional. So fundamentally, it's a measure of how much stress is on the soil, right? The size of the Mohr circle is what matters. That's, you know, the bigger the Mohr circle, the more stress there is, the closer you are to a failure envelope, and so forth. All right, now that we have these invariants, we can represent soil behavior in terms of the invariants. So what I'm going to draw here is 4 different plots, and these 4 plots fully characterize the behavior of a, say, a soil test or stress paths that happen during a soil test. So we're going to plot Q versus P prime in the upper left. That's this plot here. And kind of like how we would plot tau versus sigma prime in a Mohr circle, there's a failure envelope, right? So a straight line right there that in tau sigma prime space would have a slope that's equal to the friction angle. When we've transformed it to QP prime space, we don't call it friction angle anymore, it's different, it's called M, right? So M is basically like the friction angle, it's just represented in QP prime space instead of tau sigma prime space. Then on the upper right, we can plot deviatoric stress versus deviatoric strain. Okay, now I'm not presenting how to handle strains here. I told you how to get Q, but what I can say is that there's also a similar procedure where you take the Cauchy strain tensor and you can get a deviatoric shear strain invariant. And so that's like, you know, not the strain, not the shear strain in any particular direction, but overall for this tensor, how much shear strain has happened. And that's what we're plotting there is epsilon Q. All right, then we go down to the bottom left, and we have void ratio versus mean effective stress, E versus P prime. And I'll spend quite a bit of time in this lecture talking about this concept of critical state soil mechanics. So this framework of using invariance sets us up really nicely to understand a fairly fundamental aspect of soil behavior. For now, what I'll say is that there is a critical state line. I'm drawing it right here. And that critical state line basically is the position the soil will be in when it reaches a state of really high shear strain, really high deviatoric shear strain invariant, right? It's gone through a lot of shear strain. It's basically remolded, changed volume if it needs to, and now it's going to keep shearing without changing volume anymore. It's kind of reached a happy state where it's just continuing to shear but not changing volume anymore. So I'm writing that down here. Critical state is a condition when soil will continue to shear. Epsilon Q dot, that's the deviatoric strain rate, is greater than 0 without changing void ratio. So E dot, or dE dt, is equal to 0, which also implies that volumetric strain rate, epsilon V dot, is equal to 0. So the soil is not growing, it's not shrinking, it's staying the same volume and just shearing at the critical state. Before getting to the critical state, it will go through some kind of volume change, right? So it's going to get there eventually, but it takes a lot of shear strain to get there. All right, so here's the key concepts. All soils eventually reach a critical state at high shear strain. So you have to go through really big strains to get there. Some people have shown that the deviatoric shear strain invariant might have to reach like 100% to get there. Sometimes even at 10%, which is kind of the maximum we can do in laboratory tests, hasn't gotten there yet. So that can be a tricky thing, but eventually it does get there. Now the initial state is important. So even though it eventually gets to a critical state, the soil is going to start as generally either being loose of critical or dense of critical. And what we mean by loose and dense of critical is that if it's above the critical state line in EP prime space, it's loose of critical, right? The void ratio is higher than the critical state void ratio. That means that the soil is loose, and to get to critical state, it has to contract. It's going to get denser, right? And then it'll move down to the critical state line at failure. Okay, if you're dense of critical, it means that the void ratio is lower than the critical state void ratio, and it's going to dilate or swell to get to failure. And I'll illustrate this in just a second. I know that these concepts may be new. Okay, and then the final plot that we have is E versus epsilon Q. And this is just void ratio versus shear strain, basically. How is the void ratio evolving as the soil is sheared? Okay, now you might be wondering, how do we get this critical state line, right? I think we know how to get this one. This is basically like a friction angle. In fact, if you know the friction angle and the stress path that was used to get it, you can easily calculate M. But how do you get this one, right? How do we know this E versus P prime critical state line? Well, Malcolm Bolton, in his 1986 paper on the dilatancy of sands, gave us an equation that we can use if we know the relative density of the sand. And this is a kind of a rearrangement of his equation, not the form he originally presented it in, but if you wanted to draw that line, this is the equation you'd follow. Natural log of P prime at critical state is equal to 10 minus 1 over the relative density at critical state. Okay, Bolton formulated this in terms of relative density rather than void ratio, because you could have a sand that's fairly uniform and has a fairly high void ratio, and you shear it and the particles will have a certain behavior. Then you can fill up some of the void space with some silt that's not really contributing to the mechanical behavior of the sand, and now the void ratio has gone way down. Okay, so void ratio has a strong dependence on grain size distribution characteristics, whereas relative density is a function more of how dense is the part of the soil that's contributing to holding shear stress. So he formulated it in terms of relative density, but you can easily transform relative density into void ratio using the definition of relative density here, where Emax and Emin are quantities that can be measured for a particular sand, and then E sub Cs is the void ratio at critical state, right? So now we have a way of drawing that critical state line just by, for example, varying relative density from, say, 0 to 100%, and then computing P prime at critical state associated with those. And you can draw the line in there. All right, now let's look at how we might use these plots to interpret the data or the results from a drained direct simple shear stress path. And so we have to be pretty careful now to go back through and interpret the stress path using our knowledge of stress invariance. So here's the initial condition for a direct simple shear test, right? We have some vertical pressure. When we consolidate a direct simple shear specimen, we put vertical pressure. We don't allow any horizontal strain to happen. Therefore, the horizontal pressure in both directions is equal to K naught times sigma V naught prime. K naught is the coefficient of at-rest earth pressure. So this is our Cauchy stress tensor. Initially, before we start imposing any shear stress on the soil. Well, this initial Cauchy stress tensor can be interpreted to figure out Q naught, the initial shear stress invariant value, and P naught prime, the initial mean effective stress. And if you were to plug in these values into the tool here, right? Let's say you plugged in a particular stress tensor. Let me delete this one. 0, and you compute, right? You get 2, 1, 1. You know that these are the principal stresses. Well, then you can put them into the equation here for Q, right? And compute a value. Well, it turns out you can do this algebraically as well. And for K naught consolidation, Q is equal to sigma V naught prime times 1 minus K naught. And then P naught prime is pretty easy. Sigma V naught prime times the quantity 1 plus 2 K naught over 3. So what that means is that we start out with some shear stress on the soil. That may seem a little bit strange because we haven't started shearing it yet, but just by consolidating it anisotropically, where the horizontal pressure is less than the vertical pressure, it's under some shear stress. That actually makes some sense because when we do a triaxial compression test, the way we shear the soil is to increase the vertical pressure while the horizontal pressure stays the same. So if there's any difference in the horizontal and vertical pressure, there's shear stress on the soil. All right, then when we actively start shearing it in horizontal and vertical planes, this is what the stress tensor looks like right here. So a diagram of the stress condition, and now we're just adding a single value to the stress tensor, tau xz, and it's the same in the 1,3 and 3,1 cells. And then once again, if you go through and do the calculations, you can find that Q is equal to the square root of Q naught squared plus 3 tau xz squared. Right? So it comes out to be a pretty simple expression for a direct simple shear stress path. Now I'm skipping over some steps here, but the process is something you can follow for any kind of test. You set up the initial stress tensor, you set up the stress tensor under shear, and you can solve for these invariant values, and then you know the direction that the path is moving in Q P prime space. Now it just so happens that for the direct simple shear test, P prime stays constant if it's drained, right? If we're keeping the vertical and horizontal pressures the same, P prime will be constant. It's just going to be P naught prime. So we get vertical stress paths basically in Q P prime space. So let's come down here and look at what happens now if we have one sample of sand that's loose of critical state, right? So the blue lines are all loose of critical. What that means is that the void ratio is starting out here above the critical state line, right? The soil is looser than it will be at failure because it's starting above the critical state line. Okay, so this is really fundamental. I'm going to walk through this one step at a time. So we know that we're starting at this point. That's been specified, right? That's like specified from the outset. We know the initial void ratio. We know the critical state line values. And what we're going to do is basically, if it's loose of critical, the soil will contract the whole time. The direct simple shear stress path is vertical because P prime is not changing. So we know how it's going to go. It's going to start at this point, it's going to go down, and it will end right on the critical state line. And then we can come up to this Q versus P prime plot, and let me write in the values here. This point is equal to P naught prime and Q naught, right? So it's non-zero, and there exists a line, a straight line in QP prime space for any K naught value where you've consolidated vertically and both horizontal pressures are the same. So you're always going to start on that line if you're K naught consolidated. Then for the direct simple shear test, we're going to start there and we're going to go up to the critical state line. We're adding additional shear stress and eventually it will reach that failure line and fail. Okay, so we've gone through two of the stress paths already. Then the other two are actually pretty easy, right? We come over to, from the left to the right, the Q axis is shared, so we're starting right there at that point. And then we know what a stress strain curve looks like, right? It's going to go up, and then it will eventually plateau and go asymptotic to its final value, right? So once it has basically reached that point where Q is not really changing anymore, epsilon Q is continuing to increase, it's not changing volume anymore, that's the critical state when you reach that line. Then we can also make a plot of void ratio versus shear strain down here. Okay, and that's going to start out at the same void ratio. So we started here, we can draw a horizontal line over, and we know we're starting right there. A key to drawing these is that you have to pay attention to making sure everything lines up, right? So across the top, the Q axes are the same, everything has to line up horizontally. For the first column, the P prime axis is the same, so everything has to line up vertically. You know, be careful to draw them to where they're all internally consistent. So we're starting at this void ratio, and then it's contracting the whole time, and it will go asymptotic to a condition where the void ratio is no longer changing with time, right? It's reached a leveling off point, and then epsilon Q just keeps going up, and it's reached critical state. Okay, that one was fairly straightforward. Let's move on to one that's dense of critical. So now we're starting here at this point where the void ratio is initially lower than the critical state void ratio. Okay, and then here's one concept that you're just going to have to kind of memorize, because this doesn't really come straightforward from first principles. When you shear a soil that's dense of critical, it initially contracts a little bit, right? So it's not, it's going to, we know overall it's going to have to move up, right? It's starting down here. In order to reach failure, it's going to have to increase void ratio to reach the critical state line. But we just have to memorize that it initially contracts a little bit and then it starts going up, right? So anyway, that's a concept that you just have to commit to memory. So a little bit down, then up. Okay, and then we come here. The other thing that you're going to have to know is that soils that are dense of critical state will always mobilize a peak friction angle before they get to the critical state friction angle. And that's what Bolton's paper tells us, is that you can estimate that peak friction angle, right? We know what the peak friction angle is going to be based on his paper. So in this plot right here, let me draw in the line. This is the critical state line, so that's where the soil will be ultimately when it reaches really high strain. But there's another line right there, and this one has a slope of m peak, right? And m peak is greater than m. The critical state line has a slope of m, or sometimes m sub c, and then there's an m peak. So that's another concept you'll have to memorize. Denser critical will always mobilize a peak friction angle that's bigger than critical state. So what that means is the stress path has to go up above the critical state line and then come back down to it, right? So it goes up to mobilize this peak friction angle at that point. Let me kind of trace the path with my highlighter here. It's going to go up initially, and then it will come back down to here. So let's see. There we go. That did trace it. So up to the peak, then back down to critical. And as it disappears, you can see the path that it followed. All right, and then when we come over to Q versus epsilon Q, right, it's initially going to be stiffer because it's denser. Then it reaches the peak that's the peak friction angle value. Then it comes down and will go asymptotic to the critical state. Okay, and then if we come down, the only plot remaining is E versus epsilon Q. Okay, we're starting at this point here, and then it does contract a little bit first before dilating up to the critical state. Okay, now there's one more key concept that is in these plots that is fairly important. The peak in the stress strain curve here happens at the same point that the peak in the dilation rate happens. So if we call dilation dE d epsilon q or d epsilon v over d epsilon q, you could think of it either way. The point at which the volumetric strain is increasing the most rapidly as shear stress increases, right, has the biggest slope right there. That's going to be at the same point as the peak in the stress strain curve. Okay, dilation has the effect of actually having sand particles, if we're thinking about sand, moving uphill. And if you're having to push them uphill, you have to push them harder than if you have to push them on a horizontal plane. So the slope of the hill is like this slope, right? You can think of it physically like that. When that slope reaches a peak value, that's when it's hardest to push the sand uphill, and you're going to get the peak in the stress strain curve right there.